Okay, so should we continue? Okay, so where are we? So we did a little detour to zero knowledge, and we even showed a zero knowledge proof. Now, I know I did it very, very hand-wavy. I actually didn't plan to really teach zero knowledge, even though it's hard not to because it's so beautiful. But what I did want to, the reason I'm pointing out this, I mean, we will use it. We will touch zero knowledge some more next time. But this protocol at least has soundness half. Now let's see what happens if we apply Fiat-Shamir to it. And let's say we apply even the random oracle model, Fiat-Shamir in the random oracle model. Because remember, we started by asking, the Fiat-Shamir, is it sound? We don't know. And then we said, you know what, but if instead of actually a hash function, you use random oracle, like a completely random function, then of course it should be sound. Because what does it matter intuitively? What does it matter if the prover is talking with a verifier or is talking with a hash function? It's kind of, so if it was sound when he was talking to the verifier sends him random bits, it should be sound when you're talking to the hash function, because the hash function also sends him random bits. Almost true, but not. Why? Let's look at this example. I'm going to tell you how I can easily cheat in the random oracle model. Okay, so I have a G. It's not in the language. It does not have a Hamiltonian cycle. What I'm going to do, I'm going to hope for the best. What do I mean hope for the best? I'm going to guess your B. I'm going to say, you know what, let me try to guess what the B of the hash function is going to be. I don't know, it's a random function. Let me guess it's 0. So, because it's 0, I know I'm going to be asked to open on the cycle. So I'm going to commit to a random cycle. This is some string alpha. I'm going to go to my hash function, give him x and alpha, my g and alpha, and I get back a bit b. If it's 0, I open, I'm happy. If it's not 0, I'll try again. Again, I'm going to choose a random. I can always choose 0, or I can just choose kind of a random bit. If it's 1, I'm going to, I can commit to all zeros. Because anyway, I just need to open zeros. I'll just commit to all zeros. And then when you open, I give you pi, and I'll open the non-edges. See, it's 0. The point is, I can rerun you. In the actual protocol, yeah, with probability half, I win. But I can't, I can't tell you, okay, let's try. Oh, didn't work, let me try again. Say, no, you failed. You don't get to try again. I know that if you try again, eventually you'll win. So you got one try. But with the random oracle, I have the oracle. So I can abuse it. So I can try many, many times. And that's how I break. Okay, so what did we learn? Let's go back to the random oracle model. So first, it's not secure or not sound if PV, if the protocol has non-negligible soundness. If you can cheat with probability non-negligible, you're going to try until it works. And then you present that as a proof. So that was Leo's question, and the answer is, it's not sound. Okay, so then you say, fine. Is it sound if the protocol has negligible soundness? And the answer is no. Okay, so also not sound if protocol has negligible soundness. Okay, that seems a bit sad. But let me give you the counterexample. Okay, so let's go back to our beautiful zero knowledge protocol here. And it has only soundness half. That was kind of the complaint, right? Fine. Let me make the soundness negligible, even 2 to the minus lambda for you. Okay, how? Let's repeat it sequentially, lambda times. Okay, so we have a G. I send you a commitment of supposedly a random cycle. You send me a bit, I open accordingly. But then you're like, okay, wait, I'm not convinced. Let's try again. Fine. I send you another commitment. You send me another random bit. I reveal. Then you say, no, still not happy. Let's do it again. And we do it lambda times. Now, if all the time, every single time, I'm accepted, you're pretty convinced. Now, the probability that I can cheat is 1 over 2 to the lambda, because every time with probability half, you catch me. If I did all of them correctly, so it's very negligible. It's exponentially small. Now, I want to argue, I can cheat in the random oracle model. How? Exactly the same thing. How do I cheat? So now I have alpha 1, beta 1, gamma 1. Alpha 2, beta 2, gamma 2. Alpha 3, right? Okay. Alpha, let's start. I'm the cheating prover. I try. I guess B1 is going to be 0. Alpha 1, no, fine. I work hard. I get my alpha 1, beta 1, gamma 1. Good. Now, alpha 2, same thing. I guess beta 2, but I keep the first transcript. I don't toss it away. I keep the first transcript. And then I guess beta 2. If I guess correctly, good. If I didn't, I'm going to redo. Now, and after a constant number of times, I'm going to get the second transcript. Probably after twice, but whatever. And then I always keep the first kind of, I don't know, as many transcripts as I had, and I extend it. So I can convince you. Yeah?
What for the parallel repetition?
Very good, very good. So the question is, what about parallel repetition? Okay. Yeah?
This sequential thing is fine if you hash the entire previous transcript. Like,
no, because you can just
no?
You can just get a new
Good.
commitment until you're happy.
That's true.
Yeah. So let me emphasize. Actually, that's a very good. It's a good point that you're making. Note, when we apply Fiat-Shamir, I'm applying the hash, and what I said is, I do the same exact attack. I get one protocol. I get one transcript. Another lambda transcript. I'm done. Note that every time I hash everything from the beginning, like the hash is an alpha 1, beta 1, gamma 1, alpha 2, beta 2, but so what? I'm fine. Let's say I got the first, let's say 3 transcripts worked out. So I have alpha 1, beta 1, gamma 1, alpha 2, beta, and alpha 3. Now I'm in the 4th. I guess beta 4. I choose alpha 4 accordingly. I hash everything from the beginning, like the Fiat-Shamir hash, and I hope to see my beta 4. I see it, I'm happy. I compute gamma 4 and I continue. I don't see it. I try alpha 3 again. I don't toss my first 2 that I already did successfully. I every time extend. And the point is I can always extend in constant overhead kind of thing. Yeah?
Shouldn't that be hard for the bounded prover?
So the runtime, no, okay, so the question, look, how long does it take? I'm a bounded cheating prover. How long does it take me? Every transcript, it takes me kind of, I do constant number, on average, I do constant number of tries. On average, I do 2 tries. So it's actually quite efficient. I can generate my transcript quite fast because how do I generate it? Again, I have G, it may not have, it may have, it may not, it doesn't have a Hamiltonian cycle. I don't even know if it has a Hamiltonian cycle. Neither do I care because I'm never going to use it. What do? I choose beta 1 I guess beta 1 randomly. Very efficiently, I commit. Because if it's 0, I just commit to a random cycle. If it's 1, I commit to all zeros. That's very easy. And then I apply the hash. With probability half, I got the beta 1 that I chose. And then I can very easily compute my answer gamma 1, which is just a trivial opening. And I only need to repeat it, like it's only better with probability half. So on the overall, I won't need to repeat the same one too many times.
So that's where the non-soundness comes from, for also negligible soundness.
That is where, that's why this is not sound, exactly. So I have negligible soundness, but still it's not sound, exactly. Okay. So this is bad, but that's the only time when it's not sound. That's it. Like everything else is sound. So that goes to the question about parallel repetition. So now let me actually give you the theorem. Let's see. So the theorem is that the Fiat-Shamir paradigm is sound, finally is sound, in the random oracle model if the underlying protocol is, first it has negligible sound, it has negligible soundness, and constant round. Okay, so if it has negligible soundness and it has constant number of rounds, then it's sound. Okay, before I got negligible soundness by repeating, getting many, many, many rounds. Yeah? Oh, yeah. Otherwise, you can't even apply. If the public coin, yeah. If it's not public coin, you can't even, like, completeness doesn't hold. So I'm always talking about public coin protocols. Okay? But let me say, this is not a characterization. This is not an if and only if. We do have protocols with many rounds for which the random oracle model does apply, in particular GKR. So GKR has many rounds. So can we reduce interaction in GKR? And the answer is yes, we can, even though it has many, many rounds. And the reason why we can do it is because it sound also, or more generally, if the underlying protocol has what's called round by round soundness. I'll define it later. Maybe not today. And any such protocol has round by round soundness. But this is more general. And GKR has round by round soundness. So this is kind of in parentheses because we're not going to talk about it today. Maybe we will, we'll see. Okay, but let me first prove this. Okay, so why is it, let me do it here. Okay, so let's do the proof. So take a protocol, a public coin protocol with constant number of rounds that has negligible soundness. And I'm going to prove to you that it's secure that it's sound in the random oracle when I apply Fiat-Shamir on the random oracle model. Okay, so fix any protocol. Let's call it PV. Let's begin, let's assume, just for simplicity of notation, you'll see how it extends, that it's 3 messages. Okay, so suppose PV has 3 messages and negligible soundness. We'll later see how to extend it to more rounds. So PV, let's say there's some X. The question is in the language or not. And, they both have, so before the hash, there's like alpha. He gets back a random beta. He gets back gamma, and he chooses to accept or not. Okay, now, suppose there exists a polytime, a polysize adversary P star that cheats. I want to argue that then it means I can cheat in the original interactive protocol. So suppose there's P star and X not in L, such that the probability that P star with H and V with H, this is kind of the Fiat-Shamir, I guess, it accepts with probability at least, let's say, epsilon. I'm going to argue that then I can cheat in the original scheme with probability a little less than epsilon, but not too small. Okay, so if there exists a cheating prover that can cheat in the Fiat-Shamir version, but in the random oracle model, then I can use him to cheat in the original scheme. Okay, so how? So first note, because we're a negligible probability, this is large. Okay, so beta is public coin, it's random in, I don't know, let's call it K, but K is, it's like super logarithmic, because if there are only polynomially many options, on one of them I can cheat, so I can, this is not statistical soundness, sorry, erase what I said, let me try again. So, I can, these protocols, on one of them I can cheat. Like for any alpha, I can always find the beta for which I can cheat. Otherwise, if I can't cheat on any beta, there's no point in doing interaction to begin with. I'll just give you alpha and a fixed beta, I'll give you gamma, and that's it. So in these protocols, there's always betas for which I can cheat on. And therefore, because I have negligible soundness, beta must come from a super polynomial universe. If it's only polynomial, then I can play the same game that I did before, kind of hope to succeed. It's like too bad in Hebrew we have a very good saying for this, like, you know, the hope, when you cheat with the hope of not being caught, there's a word for it. But yeah, Americans are too, they don't cheat, so they don't have words for this. What?
Like a con?
Is that a word? Okay, I'm not from a con.
As in like confidence man.
Oh, I see.
You like are lying to someone?
Exactly.
Like,
yeah. Exactly. Yeah. Okay. So suppose there exists fake it till you make it. Exactly. Totally. Okay. So suppose there exists a cheating prover. Okay. Now, how does he cheat? Let's see what this prover does. This prover gives you this prover outputs. So this prover outputs some alpha, beta, and gamma. That, like a transcript, right? And this beta is hash of x and alpha. That's how he cheats. That's a valid transcript. That's a transcript that will such that the original verifier accepts, right? So in the Fiat-Shamir, the prover, he just outputs this, and the verifier checks that beta is indeed h of x and alpha, and that this is a valid transcript. Okay. Now, the cheating prover, he sends oracle queries to his hash function. Now, this prover is bounded. He's polynomially bounded. Let's say he sends, suppose that P star sends, I don't know, Q queries to the oracle, to H. Okay, he's bounded, so he runs in polytime. So what does he do? He has oracle access. He's trying to cheat on X. Now he can ask his oracle, okay, here's alpha 1, give me beta 1. Here's alpha 2, give me beta 2. He said that most polynomially many queries because he's polynomially bounded. So there's some polynomial Q queries that he sends to H, and let's denote them by alpha 1 up to alpha Q. Okay, now first thing, note that the probability that he succeeds in generating alpha, beta, gamma, so that alpha is not one of the queries, is negligible. If he didn't ask, how does he doesn't know what beta is. The only way he gives beta, which is the right H, is by asking. He has no idea what beta is. And so if he didn't ask, he can guess his probability like 1 over 2 to the k. Okay, so maybe I'll go here. Continue here. So first thing, note the probability that alpha, beta, gamma are accepting with x. So meaning the verifier accepts them, and alpha is not alpha 1 up to, it's not one of them. This probability is negligible. And this is because k, and this is because, or it's, yeah, it's like something like 1 over 2 to the k. What? Sorry, alpha q. And sorry, what did you say? Oh, no, alpha, x alpha, yeah. Right, but alpha needs to be one of the alpha ones. Sorry, yeah. So he sends, okay, he sends kind of x comma alpha 1 up to x comma alpha k. That's kind of what he sends. I mean, he can send other ones, but then, yeah, it shouldn't help him. So, it should be one of the queries he asked, first of all. Because if he didn't ask that, he has no idea what the beta is. So he guesses the beta correctly. It's probably 1 over 2 to the k, and that's negligible. Okay. So this means that if he succeeds with probability epsilon that's not negligible, almost with this probability, or with probability epsilon minus negligible, he doesn't only succeed, but he succeeds with alpha that he queried. So now I'm going to use him, because I know that he succeeds with alpha that he queried, I'm going to use him to cheat in the interactive protocol. Okay, again, I'm really abusing the random oracle model, because I'm assuming that the verifier, really the only way he interacts with the oracle is by kind of queries, and I know the queries, and I can use it to kind of cheat. So let me now construct P double star that cheats in the interactive. In the interactive protocol. Okay. How do I cheat in the interactive protocol? Okay, so first I'm going to give the same x with x. The same x. So this P star succeeded with some x in the language, I'll use the same x. Now, first thing I need, so here I am, P double star, I'm ready to go. Here's x, v. I need to start sending alpha. What do I do? Which alpha do I send? Now, what do I know? I know that I want to use this guy. I can't cheat. I'm going to use him. He's a cheater. I'm going to use him. What do I know about him? I know he cheated with alpha, beta, and gamma. And one of these alphas he used as a query. Okay, which one I don't know. But here's what I'm going to do. I'm going to guess randomly. And what's the saying again? You fake it till you make it. I'm going to guess randomly and hope. Okay? So what I'm going to do, I'm going to guess. So what does P star do? First, I'm going to guess a random I in Q. So just the index, so I know he's going to make Q queries. I don't know yet which queries. But let's say I have a bound on his runtime, so I have a bound. So P star there runs in time at most Q, let's say. So he queries at most, he makes at most Q queries to the oracle. That I know. I'm going to choose a random index, like supposedly a random query, one of the ith query to his oracle. And what I'm going to do, I'm going to send here alpha I. Now, what is alpha I? I don't know what alpha I is, but don't worry. What I'm going to do, I'm going to simulate the oracle from him. So I'm going to pretend I'm the random oracle. Okay, I'm going to start by saying, okay, P star, I'm going to use you. Yeah, let's start. You gave me X. Send me alpha. Like, generate this. Generate alpha, beta, gamma. Now, what does P star do when he generates? He's like, okay, let me think. Alpha 1. I'll give him a random beta 1. Okay, alpha 2, or X alpha 2. I'm going to give him a random beta 2. Alpha 3, random. Alpha 4, random. Until alpha I. Once I get alpha I, I'm happy. I'm like, ha, alpha I. I'm ready, alpha I. I get a random beta back. What do? I tell him, oh, your answer from the oracle is beta. Okay, so I'm simulating P star's oracle in my like I'm behaving like I'm the oracle sitting on top of P star. Okay, he gives me alpha 1. I'm giving sure here's a beta 1. That's your answer. Alpha 2, beta 2, alpha 3, beta 2. Alpha I for random I, it's beta. Now he gives me gamma. Now, okay, now he gives the answer. And I continue. Alpha I plus 1 random, alpha I plus 2 random. Okay. At the end, he gives me a transcript. But with probability 1 over Q, it's with my alpha I. If he uses with my alpha I, hooray! I'm going to give the gamma I. If it's not my alpha I, I'm going to, fail. Well, going to try again. Then I fail. So what is the probability? So that's my protocol. So if he didn't cheat with the gamma I, with the alpha I, if this alpha is not alpha I, I'm going to, lose. I'm going to say, sorry, I failed. What is the probability? So guess, and then simulate the oracle for P star randomly, except for alpha I simulate via the verifier. For alpha I, answer with beta. That's all. And then if alpha, beta, gamma is such that alpha equals alpha I, then, then I guess let's call this gamma. Then send gamma. That's the protocol. That's the cheating prover. That's P double star. Now, what is the probability that P double star is accepted? Again, what does P double star do? P star is accepted with probability epsilon. So with probability epsilon, he gives me alpha, beta, gamma. But he chooses alpha after querying, he chooses this after querying the oracle Q times with different alphas. Let's say with all of them he uses the same X, otherwise he's stupid. But whatever, it doesn't really matter. We established that except negligible probability, one of these alpha is in the ith query. So what is the probability that I succeed? Very nice. So the probability, great. So the probability, I'm out of space. So the probability that P double star is accepted is at least the probability that P star is accepted over Q. If he's accepted, if he chose alpha I correctly, but it's random. One of them he cheated with, and I choose it randomly, so it's probably at least 1 over Q. And minus the negligible, which is kind of minus, I guess, 1 over 2 to the k, which is kind of the probability that he didn't even guess. He just, the alpha is kind of, he just didn't use one of the queries, but that's really small. So it's still pretty big. So there is a loss. There is a loss of Q. But Q is polynomial, and if alpha is non-negligible, then alpha over Q is also non-negligible. And that's a contradiction. Any questions?
where we actually use like the random oracle model, like where we couldn't have just put in another hash function. It's like that top line there.
It's not yes, it's this top line there, but also that the fact that we even have alpha 1 up to alpha, the fact that we can say that there exists alpha 1 up to alpha q, like the fact that we're able to observe what he knows about the hash is in the random oracle model. So the proofs in the random oracle model, it really means, one needs to be careful because people want to, okay, what's the kind of, so, okay, the intuition or the intuition behind the random oracle model is to say, let's try, what do we need from the hash function? We want it to kind of look random. We want it to look random because the verifier's message are random, we want also to look random. And now, okay, because we look random, and that was kind of the motivation for this random oracle model. And then it's tempting to say, so now all we need is a hash function that kind of behaves randomly. Let's try to use, I don't know, like people say, like pseudo-random functions, which were not defined here, whatever. Okay, but you can, but who knows what the, how will you prove soundness? This proof, unless really the prover, what it does is really just runs the function. If all he does, if the cheating prover, all he does, he gets the function, he's like, this really looks like crap, I don't know what to do, I'll just feed him inputs, see what output I get, that's the only thing I can do. Then this proof in the random oracle model makes sense. But as long as he can do anything else, besides like blindly feed an input, get an output, I don't have a proof. Yeah?
Why do you have 1 over 2k?
Oh, 1 over 2 to the k? Yeah, the only reason I added this negligible fraction here is there's 1 over 2 to the k probability, which is tiny, that p star is accepted with none of the alphas. So maybe it just chose alpha that was not queried at all. But, he managed to choose beta randomly, which happens probably 1 over 2 to the k, because beta should be h. And if he didn't ask h, then he doesn't know what beta is, and beta is random. But there is that probability that he chooses alpha that's not one of the q. So here, if he chooses one of the q, I guess the one he chooses correctly is probability 1 over q, so I get epsilon over q. But if, I guess I should put here, yeah. But if he chooses randomly, then like I'm out of luck. Yeah.
Q.
Good. How do I know Q? Very good question. I actually don't know Q, and the Q even can be a little bit adaptive. So maybe this cheating prover he sends alpha 1, and depending on beta 1 that he gets, he decides how many queries he wants to add. Maybe he's very happy with his beta 1 and he's done, and maybe he's very unhappy and sends another. So the number of Q can be adaptive. But since P star is fixed, and I know his polynomial time, so let's say the runtime of P star is lambda squared, lambda to the third. I know that he cannot ask more than lambda to the third queries, because each query takes 1 unit time to ask. So I can upper bound the number of queries by the runtime of P star. So really, the probability that is accepted, if I have no idea what Q is, and in the worst case it's the runtime, it's kind of epsilon over the runtime of P star. Which that I know, because I'm giving P star, let's say, as a circuit.
Have a circuit that doesn't halt?
No, but I'm promised that P star is polynomial size. I know it halts. So my contradiction assumption is as follows. Suppose there exists a Pauli size, I don't know, lambda to the third size, P star. Now I know that lambda to the third asks at most, that P star asks at most lambda to the third queries. I think of the circuit of P star as being a circuit that has kind of H gates, like random oracle gates. So you can feed it like alpha or x and alpha, and out comes, and it's like one gate. It's like one time unit. But he cannot have more than lambda to the third of them because that's the size of the circuit.
So like, does the circuit like not have loops?
No, it doesn't. No. It doesn't have loops. It's like yeah. No, I mean, it can have it. The runtime is fixed. Like it can compute at most lambda to the third gates. It has lambda to the third gates in it. So any other questions? Okay, this was 3 rounds. What about more? So what if you have like I don't know, a C rounds? What happens then? Any guess in how the probability decays with a number of rounds? Yeah?
Like epsilon over q and then c over q.
Exactly. Yeah, exactly. So it's going to be, if you have C rounds or C messages from the verifier, let's say, if you have C messages from the verifier, it's going to be something like epsilon over q to the C. And to see why, it's just, it's really the same argument. What we need to do is suppose that in each round, P star sends at most Q queries. So maybe he sends a Q queries of the form alpha 1, like x comma alpha 1. And then he sends Q queries of the form x alpha 1, beta, like x alpha beta. And then he sends, x alpha beta gamma. And then he sends Q queries of the form x alpha. So Q query for each partial transcript, he has Q queries. Now, if you have C rounds, you need to guess correctly for each partial transcript the correct I. I'm going to guess that, so I'm not going to write it down, but like, because it's really the same, but let me just say it in words. P double star, what he does is for every round of the verifier, he guesses the index of the query, he guesses the index of the kind of the hash, the query to the hash function, which is going to be used in the proof. Okay, so he's going to guess, and here we said you guess I. Now we're actually going to guess I1 up to IC. Okay, for each message of the verifier, we're going to guess an index. And now we again just emulate P star exactly as before. So how do I emulate? I go to P star. He asks me just alpha 1, like if he asks me just of the form for the first message, like alpha 1, alpha 2, alpha 3, I give him random, until he asks for beta, for alpha I, and then I give beta I. Now, in between, he may ask for bigger. He may ask all of a sudden for x comma alpha beta gamma random. Then random, I give everything random. But the first point I get alpha, the ith query for like the first, corresponding to the like transcript, like the first message, then I'm like, aha, I got it, alpha I, thank you very much. I put my alpha I get beta, I enter beta as kind of the answer from the oracle, and now I'm happy. Now I start counting how, like for I2, I start counting how many messages are the form alpha beta and some gamma. Alpha beta gamma 1, alpha beta gamma 2, alpha beta, until I get to I2. All of them I answer randomly. Once I get, and any other queries for that, I don't know what form, random. Once I get to the like alpha beta gamma I2, like the I2, I'm happy. I run here, I put my gamma, I get a delta. I answer with delta. Now I start counting how many queries of the form alpha beta gamma delta, epsilon. Epsilon is fixed. Next one. I count until I get I3. And the I third of them, I give the answer, I just do it for as many rounds as needed. But for me to be sound, I need to make all these guesses correctly. And each guess is going to be probability Q. So that's why kind of the probability decays a lot. Yeah?
So does that mean that if like the number of rounds is like log security parameters, you're still secure?
Yeah, good. No, it's not. Okay, if the number is log, it's almost secure, but then the probability is Q to the log. It's not 2. Q is not 2. So you'll get a little negligible. However, so it will be negligible, but not too negligible. It's going to be kind of quasi-poly, like 1 over quasi-poly. So if you have log rounds, if you happen to know that the original interactive protocol has soundness less than quasi-poly, like sub-exponential, let's say you have the guarantee that a cheating prover cannot cheat except with like 1 over sub-exponential probability, then log rounds will be good. So the number of rounds, see, this is really your probability of cheating. And as long as your interactive protocol has the guarantee that you cannot cheat with this probability, then you have a proof. Yeah? Yeah?
Could you replace formula Q to the power of C with Q over C to the power of C? Because we distribute Q currents. So.
Good. Yeah, so the question was, can we maybe replace this by Q over C to the power of C, because Q is the total number of queries. The thing is, so okay, I'll tell you it's not that simple, because we don't know exactly how many, so suppose the prover total asks Q queries. We don't know how many queries he has. Maybe he has all of them on the first message, and then just one. And it can be adaptive. It can depend on his answers. Maybe he asks alpha 1, he gets beta 1, he's happy, he's not going to ask again, and all the answers are going to be in the second messages. Or maybe he sends alpha 1, beta 1, he's so unhappy, all the Q goes for the first message. So how do you choose the I? Like, how do you choose? For me, like I said, let's choose them randomly. But you may be able to do better. I didn't, one can think, can you do better than this? Possibly, because you're saying, don't forget about the end. Like the end, it's not gonna, most of them, you won't go all the way to the end, so you can probably choose it more from the beginning. Probably you can improve on this. I didn't do the calculations, because usually we don't really care about constants, but you're saying, oh.
There's something weird, because if you make C equal to Q, then it's going to be 1.
That's why it's not true in general. Like in general, you can, but you probably can improve it a little bit. You know what I mean? Because, yeah, maybe you want to choose it in a different distribution, not randomly. More towards the beginning, because most of them are not going to be at the end. But yeah, there are probably optimizations that can be done. Great questions. Any other question? Okay, so let's see. So maybe I will do then, I'm debating if to go to the soundness in the standard model or to do the round by round. You know what, I'll do the round by round soundness, because I want to...
So this says Kilian.
Oh, good. Yeah, thank you. Okay, good. So what did we prove? So we proved that the random oracle model is sound. The Fiat-Shamir applied to the random oracle is sound if you have constant number of rounds and negligible error. Now, Kilian-Micali protocol has constant number of rounds, 4 to be precise, and negligible error if you take the PCP with negligible error, which you can we have PCPs with negligible error, you put it in and you have 4 round negligible error, you apply Fiat-Shamir in the random oracle model, it's sound. So Fiat-Shamir is sound in the random oracle model for Kilian-Micali. That's great. As I said, we don't have so now you can ask, do we have a proof of Fiat-Shamir for Kilian-Micali in the standard model. Okay, in random oracle model we have. How about standard model? And this is important because for a long time, people believed that if we have a proof in the random oracle model, it means there must be some hash function for which this protocol is sound. Namely, the belief was, if you have a proof in the random oracle model, and then if you use it with Fiat-Shamir, something goes wrong, like someone breaks it, we need to blame the hash function. Exactly, you've used a bad hash function for Fiat-Shamir. Okay, so typically, when Fiat-Shamir is used in practice, it's used, let's say, with SHA-256, that kind of a standard off-the-shelf hash function that's used. And now, if someone ever breaks your your protocol, the conclusion was SHA-256 is not a good hash function. Use another hash function. Okay? However, this protocol is an example of a protocol. It's very natural. It's great. Like it was invented not as a counterexample for Fiat-Shamir, yet, and it's secure in the random oracle model. So Fiat-Shamir is secure in the random oracle for this protocol, yet there are hash functions contrived, but there are contrived hash functions such that this protocol is insecure no matter which it's not secure in the Fiat-Shamir for any explicit hash function that you use. It's secure in the random oracle model, but is not secure with any actual function family. So what we learned from this is the random oracle model is a nice sanity check, but it's really not a proof. I mean, we knew it's not a proof, but it doesn't even guarantee that there exists a proof. It's just a minimal sanity check. Yet, let me tell you, in practice, actually, that's how people check that things are secure in the random oracle model. If it verifies this check, they use it. And as far as I know, things never broke because of the random oracle model being insecure. So it's more of a theoretical kind of interesting thing, but actually in practice, it's not an issue. Yeah?
Try to break.
Yeah, so, okay, the question is anybody trying to break? The answer is, okay, things are broken all the time. Okay, things are hacked and broken all the time. It's very rare that what's broken is actually the crypto. Okay, it's not the crypto that's broken, but people do try to break. For example, one thing that often people they use to break is our cryptography uses randomness. We use randomness in our crypto. And in practice, people don't use, we use secret keys. We assume our secret keys are random. But in practice, where do you get this randomness? And often, the implementations are not done well. And somehow, guess what? Things turned out not to be random or not random enough. And then things are attacked. So things are attacked a lot, actually, in practice. There's a lot of breaches, security breaches. But it's very rare that it's in the crypto itself. Now, why is it not done in the crypto? One would believe that just because the crypto is actually secure. And, it's the implementation that are the problem. And how many people are trying to attack the crypto? It's very hard to say, but my guess is that in NSA, there's a lot of people who are working really hard to attack the crypto. But these are done behind sealed doors. So I remember there's a fantastic guy who's Shafi Goldwasser's student in our community his name is Joe Kilian. And he was a professor and he moved to NSA. And I remember once I asked him a long time after he was already at NSA, I asked him, so, do you guys know how to factor? And he told me his answer was, the worst part about my job, I'm not allowed even to joke about these things. So, so the answer is we don't know.
We don't know if they don't know.
Yeah, exactly. Okay, any other questions? Yeah.
This is is kind of general, but like in general, do you think like private, like the NSA and like private, like cryptography, I guess, has like is further than like what's publicly known? Or?
The question was, do I have a guess?
Yeah.
So I do not know. So let me rephrase your question is, do I have a guess as to if the NSA knows more than we do? My guess would be yes, because they know everything we know, because we don't hide anything. And they have smart people, so why won't they know a little more, you know? Do they know how to factor? That I don't know. Like, do they have, like, is their world hugely different than ours? That I don't know. But I'm sure they probably have something better than we know, than we do. And we've seen it in history. Like, I think even RSA was invented, but actually was privately known before. So we know examples. So probably today too. But it is kind of, I wish it'd be nice to know. Yeah.
The people publish like negative reports saying like we tried to break this random oracle protocol with SHA-256 and
That's another thing. No, people don't tend to publish their failures. So it's very hard to know, going back to your question, how much did people try? When we say, look, there's no break, okay, what does that mean? Are there it means we don't know of a break. It doesn't mean there's no break. We don't know of a break. Okay, how much did we as a community try to break? It's very hard to know because, exactly, your question was a very good one. People don't say that, don't report how many hours they tried to break and fail. So we don't know. Yeah.
If you do break something, are you not supposed to like publish it? You're supposed to like tell that anything privately and then like wait like 6 months and then because it might be dangerous.
Oh, you're saying if you do break, maybe you need to be careful to publish it. Yeah.
So maybe people break something all the time, but like no one ever.
Never know. I actually don't. I know. So I don't. My job. I don't. That's not the art I kind of do. I don't usually break schemes. I like to kind of construct things. I don't work on trying to break. But I know from like folks here that do more security work, and it's like people get in trouble for breaking, for publishing and breaking things. And I don't know, we talk to them, they always mention the word jail in their conversations. It's like, wow, okay, try to stay out of jail, They're like, okay, no. And, here in theory land, it's pretty easy to stay out of jail. They don't run after us. But yeah, this can be a dangerous business. Any other questions? Okay. I'm trying to think if I want to, maybe I'll end with a round by round soundness. It's not as interesting, but let me just say a few words on it because just so I can check the box. I think it's in, yeah.
So what was the verdict on the zero knowledge proof? You cannot do it in parallel?
Good, okay, so the question was, going back to the zero knowledge, we said, okay, so zero knowledge, if you repeat it sequentially, it still stays zero knowledge. Okay, it still stays zero knowledge because exactly the same reason as before. Each time, I can simulate. Essentially, I can simulate this transcript exactly the way I can kind of attack it in the random oracle model. It's like every time so remember, what is the definition of zero knowledge, which I believe I erased? Look at this. I didn't. Okay. So I want to say for every cheating prover, for any cheating verifier, I can simulate the transcript. If I repeat it in parallel, I can simulate the transcript. How? I commit. I'm the simulator. I'm going to simulate a transcript for you. I commit at least a physical transcript with commitment as a safe. I commit. I fake it till I make it. I guess beta 1. I commit. I hope V star, and then I compute V star's answer on my commitment. Hope it's beta 1. If it's beta 1, I can open, and I continue. If it's not beta 1, I try again. And that's how I simulate the protocol exactly as I cheat in the random oracle model. What happens when things are sequential? When things are sequential, when things are parallel, when things are parallel, now In the parallel world, you get alpha 1 up to alpha lambda. So lambda parallel partition of the commitments. So you commit all the matrix, kind of all the commitments, alpha 1, you commit, you do it in parallel. You get all the beta 1 up to beta lambda, tells you if to open with respect to 0 or 1. And then you need to do all the openings, gamma 1 up to gamma lambda.
The thing that helped you
Wow.
simulate also helps you break the wrong.
Yeah, exactly. The thing that helps me simulate is exactly the break of the random oracle model. Exactly. Exactly. Now, what happens if I do it in parallel? If I do it in parallel, it's not, okay, if V star was honest, was completely honest, then yes, I'll just simulate each one separately, because I can do the same thing. I just choose these, like each one randomly, simulate. The thing is, V star may be malicious. Here's a really problematic V star. Suppose V star is such that I give him all the commitment, so it's digital. So I told you in a safe, but actually there's cryptography going on in there. Let me just gloss over the crypto. The safe is going to be digital, so there's just bits. And now suppose V star chooses beta and some function of alpha. He applies he's a cheating verifier. He wants to learn. His goal is to learn. And how does he learn? He gets all these things. He applies some function f to all of them together. Think of it like a random function. I don't know, and gets beta 1 up to beta lambda. And that's what he sends me. That's the cheating prover. Now, how do I simulate this? I can guess beta 1 and try to get this. I can't guess all the betas at the same time. The thing is, I can try to guess beta 1, give a commitment here, hope for the best. But the problem is, if I do alpha 2, the beta 1 may change, because the betas are a function of all the alphas together. It's really not clear how to simulate this. Okay. So the question holds, is this zero knowledge? And this was an open problem for a very, very long time, over 20 years. We had no idea. People really tried. This we know because people did publish some partial results, and we all were, like everybody worked on it for a very long time. We shared our frustration. And then in 2019, actually here at MIT and BU in our neighborhood, a bunch of people, I'm going to tell you about it, actually proved that this is not zero knowledge. Not parallel zero knowledge. And the interesting thing, the way they proved that it's not zero knowledge is actually by proving that the Fiat-Shamir is sound for this protocol, which is very weird. Okay, so what they proved is that this protocol, this is a 3-round protocol. You can apply Fiat-Shamir to it. What they proved is, there was a question, is Fiat-Shamir sound, in the standard model, is it sound, nobody knew. They gave kind of a breakthrough result, showing it's sound in the random oracle model. So that's what I'm going to show you next time. Next time, we're going to prove that this protocol is actually sound if you apply Fiat-Shamir to it. The interesting thing is, the fact that it's sound, if you apply Fiat-Shamir, shows, we're going to show this is sound. So of course it's sound. I mean, if you just do parallel partition, you'll get soundness. But it's also sound there exists a hash function. So there exists a hash function such that even this hash function under a standard cryptographic assumption known as learning with error, we'll talk about later, almost learning with error, with circular security. Never mind, there's a standard cryptographic assumption, so that under that assumption, there exists a hash family, such that this protocol, this protocol is is a Fiat-Shamir sound. So it's sound even after you apply the Fiat-Shamir paradigm to it. Yeah?
You're talking about the Hamiltonian passing energy, that specific protocol,
Yeah.
and like not just any zero knowledge.
No, not any. There may be zero knowledge protocols that are, you can repeat in parallel, and zero knowledge may, yeah, sorry, let me clarify. I'm not saying that any zero knowledge protocol, if you repeat it in parallel, it's not zero knowledge anymore. I'm not saying that. I'm saying that this specific protocol, for graph Hamiltonian, if you repeat this protocol in parallel, it's not going to be zero knowledge. And the reason it's not going to be zero knowledge, which is, this is kind of, should be really like, what? You should not understand what I'm saying, or at least it takes time to absorb, or at least to me it took time to absorb, is the reason it's not zero knowledge is because actually this protocol is secure if you apply the Fiat-Shamir. It's sound if you apply the Fiat-Shamir paradigm to it. And this is what we'll see next time. So this is weird. Yeah?
Just because it's not simulatable, like you can generate it in that order.
Exactly. So why, exactly. So why is it? Why is it not zero knowledge? So what does it mean to be zero knowledge? It says, what's the definition of zero knowledge? Zero knowledge says for any V star, you can simulate. But now I'll be the V star that you cannot simulate. My V star, I'm going to be a Fiat-Shamir V star. I'm going to compute my beta. I'm V star. I want to learn something. My goal is to learn something. So I don't want to be able to simulate you, then I didn't learn anything. My goal is just to learn. So how do I learn? I'm going to choose my betas as a Fiat-Shamir. I'm going to use the Fiat-Shamir hash. So you told me it's sound. There's some hash family that it's sound. Great. I'm going to choose a random hash key from this family, and my beta is going to be hash of alpha. Now you're saying you can simulate me. For any x, you can simulate me? If you can simulate me for any x, then you should be able also to simulate me for x in the language and for x outside the language, because you don't know which is in and which is out. You're Pauli bounded. Yeah? So let's say I want to argue there's no simulator. Okay, let me actually say this slowly, so I'm not going to do this round by round soundness today. It's not that interesting. But it will come maybe to haunt us later. But let me, it's nicer to do it. And we'll just end with that. We have a couple minutes left. We'll just end with that. Okay, so again, next time we'll see that parallel repetition of this specific protocol with a specific commitment, okay, with a specific say, digital safe, is sound when you apply the Fiat-Shamir to it. Okay? Now, here's the claim. Soundness, or Fiat-Shamir soundness, implies that it's not zero knowledge. And let me argue that. So here's the proof. Suppose it's zero knowledge. Okay, so suppose it's wrong. Suppose I'm going to get a contradiction. So suppose there exists a simulator, a PPT. There's an efficient simulator such that, I'm just copying the definition. Suppose it's zero knowledge. It means that there's an efficient simulator such that for any Pauli size V star, for any cheating verifier, and for every x in the language, you can simulate. Okay, so for every V star and for every x, sim, what does sim do? Sim, an input x, outputs like alpha, beta, gamma that are accepted with respect to x. Okay, because the prover is accepted, he's honest. So the prover is always accepted. You're talking with an honest prover that has a witness. Okay? So he should also accept. They're indistinguishable. Real and ideal are like the real view should be distinct from the real view should be distinct from the simulated view. The real view output something that's accepted, so the simulated should output something that's accepted. Okay. Now, so first, I want to argue this implies that also for x not an L, or for random, I should say, or there exists at least, such that sim and x also outputs alpha, beta, gamma that are accepted. So this is accepted. I'll write it like this. And so this should also be accepted. Why? Why? So I want to argue if for every x in the language, this efficient simulator with ORC access to an efficient verifier output an expected transcript, there must be at least one x in the language so that he outputs something that's accepting, because he can't distinguish in the language. It's a hard problem, and he's efficient. If all the time that it's in the language, he outputs accepting, and all the time not in the language, then the simulator broke your language. He broke NP. Okay, so that can't be. So there exists x not in the language for which he manages to generate valid transcript. That breaks the Fiat-Shamir, because what does V star do? V star, this means that this is hash of x and alpha. That's my V star. My V star applies the Fiat-Shamir. The V star that I'm interested in is the Fiat-Shamir V star. We assumed that the Fiat-Shamir is sound with respect to some h. This V star is going to use that h. He's going to choose a random hash key, and he's going to choose, that's how he chooses the beta. Or he's going to fix a random hash key is fixed, that's it, that's the hash key. It's fixed. Now sim has to use that hash key, because otherwise you can distinguish. So he broke the Fiat-Shamir. That means he cannot simulate. There's no simulator. A simulator will break the Fiat-Shamir. So it's kind of an interesting people believed, it was a weird state of the world, because people believed that, in some sense, that parallel zero knowledge should hold. Why not? You can't learn. What can you learn? Try to learn. But people also learned that Fiat-Shamir is true. But these two are not, you can't believe both, you know? And it wasn't clear which one is the right thing. And so now we know, at least for this protocol, Fiat-Shamir is true and it's not zero knowledge. Yeah?
We actually does it show something stronger, like that any non-interactive proof cannot be zero knowledge? Is that basically what's
any interactive proof for which Fiat-Shamir holds cannot be zero knowledge. Exactly. Yeah.
Okay, so yeah, because if you use like a specific instantiation of a hash, then it's only equal kind of the hash key and nothing else.
Exactly.
So there's no interaction that breaks zero knowledge.
Yeah.
Exactly. That's what the proof I see in the past.
Yeah. Okay, we're out of time.